It started like something out of a routine night shift, a faint flash in a wide field survey, an extra dot on an otherwise familiar star map. At first it looked like every other transient that gets cataloged and then forgotten, a tiny visitor on a long, lonely path through space. But almost immediately, the tiny visitor stopped behaving like anything we had seen before. What astronomers first logged as a new interstellar incoming object would soon force the scientific community and the world to renegotiate what it means to be watched by the cosmos. On July 1, 2025, a team scanning the skies flagged an object moving through the inner solar system. It received the dry, clinical designation 3I/Atlas, the third recognized interstellar interloper in modern observational history, but that label concealed the way it would come to upend expectation. Initially, the object looked familiar, compact, bright, with a coma that suggested volatility and a tail that implied outgassing like any cometary visitor. But as telescopes trained on it, as instruments that have long been the workhorses of planetary science assessed its behavior, something didn't add up. Comet tails should stream away from the sun. Solar radiation exerts pressure on tiny particles, driving dust and gas outward in an unmistakable pattern. The tail always points away, trailing the nucleus like a streamer behind a swimmer. What Atlas displayed was the mirror image of that rule. Its plume pointed sunward, not away. Frame after frame from different observatories, independent instruments, different continents, all showed the same persistent, narrow jet of material projecting toward Sol. It wasn't a diffuse, fan-shaped coma. It was a columnated, relentless arc aimed at the star. The picture was at once perplexing and persistent. Observers began to whisper about perspective errors, data artifacts, and camera defects. But those early explanations didn't survive scrutiny. Gemini South, the very large telescope in Chile, the Lowell Observatory, and images from space telescopes all confirmed the same ghostly phenomenon. The chemistry only deepened the puzzle. Spectroscopy conducted by the most advanced instruments available revealed a chemical fingerprint that deviated sharply from the cometary norm. Water vapor, the common backbone of solar system comets, was not the dominant volatile. Instead, carbon dioxide ruled this object's atmosphere by a margin rarely, if ever, observed. CO2 abundances that outstripped water by ratios that sat many standard deviations outside what we consider normal. On top of that came a pronounced presence of atomic nickel and an almost complete lack of iron vapor, a strange and lopsided elemental palette that didn't map onto the file of known cometary compositions. This was chemistry from a different nursery, a different set of formative conditions that freeze, trap, and eject elements in unfamiliar ways. Beyond chemistry and optics was something even more consequential: dynamics. As analysts dug into positional data and fit ever more precise orbital solutions, they encountered residuals, small, systematic differences between predicted positions and observed ones, that could not be reconciled by gravity alone. When the models allowed a tiny non-gravitational acceleration pointed sunward, everything fell into place. The magnitude was small, on the order of 4 times 10 meters per second squared, but over days and weeks, that small push accumulated into shifts of thousands of kilometers. In the context of spacecraft dynamics, that acceleration sits in familiar territory. It is comparable to the gentle but persistent thrust produced by ion drives. What made it unnerving was the combination of thrust-like acceleration with a plume that behaved like a directed exhaust. Narrow, steady, and coherent, not the messy, turbulent stream of dust we expect from sublimating ices. Scientists began to draw analogies publicly and privately. If an object wanted to decelerate as it fell into the inner system, firing a jet sunward near perihelion makes physical sense. You maximize the Oberth effect, shedding kinetic energy most efficiently when speeds are highest. That's a trick our own spacecraft use. The data from Atlas suggested the same tactic. The plume's geometry, the alignment of the acceleration vector, the spectral evidence for ionized species, all implied engineered behavior, or, at the very least, a process that mimics engineering to a degree that natural mechanisms struggle to match. This was not simply another curiosity. The orbit itself was startling. A retrograde, hyperbolic path, eccentricity well over 6, slicing through the plane of the ecliptic with an alignment that brought it tantalizingly close to several planets in sequence. The chances of a random interstellar object threading a path that skirts Mars, brushes Venus, and then swings by Jupiter within narrow windows? Calculations placed it at odds with coincidence by orders of magnitude. It looked like a corridor, a flight path, something plotted to make the best use of gravitational assists and planetary geometry. An object that appears engineered to use planetary gravity hints at purpose, at mechanics that go beyond mere accident. And then there was timing. Atlas was scheduled to pass behind the Sun on October 30th, 2025. Solar conjunction is the astronomer's blindfold. The Sun's glare and radio interference cut off direct observation and telemetry from Earth for a period that can range from days to weeks. And crucially, it's the perfect environment for a maneuver to go unseen. If an object wanted to change course without immediate detection, slipping out of view, behind the Sun, and performing a burn there would be ideal. The mere coincidence of a potential propulsion signature and an impending conjunction was enough to raise alarms on nearly every major planetary defense and space science team. When James Webb and other high-end observatories turned their instruments to the Traveler for spectrographic study, they found signatures that read like propulsion rather than random sublimation. The plume consisted of particles with a narrow range of velocities, a monoenergetic signature reminiscent of ionized exhaust streams. While xenon, the propellant of choice for human ion thrusters, was not detected, the chemistry present could be ionized and accelerated under the right conditions, producing a focus jet. The distribution and velocity dispersion of that plume were inconsistent with passive outgassing. It was controlled, tightly collimated, and sustained. Given those facts, a subset of researchers proposed a radical hypothesis. Atlas might be a probe. Not in the sense of an alien spacecraft performing overt contact, but as an autonomous scout of a type any civilization might employ. A sensor, perhaps, designed to enter other star systems, take measurements, and adjust course as needed. If one imagines a network of such devices, a lattice of silent observers drifted through the galaxy, then Atlas could be a node in a pattern that we are only now capable of seeing. And that idea gained traction when analysts at JPL and other centers began to do something unusual. They compared Atlas's inbound vector and trajectory with those of the two previously cataloged interstellar visitors, Oumuamua from 2017 and 2I/Borisov from 2019. Taken alone, each of those objects had been puzzling in their own ways. Oumuamua with its unexplained non-gravitational acceleration and peculiar shape, Borisov with its chemistry that resembled comets, yet came from outside our system. But overlaid with Atlas, an unsettling pattern emerged. Researchers found echoes in the orbital geometry, alignments, mirrored vectors, corridors through the ecliptic that seemed less chaotic and more like a planned route. The technique, dubbed orbital fingerprinting, borrowed methodologies from satellite forensics. Look for correlations and repeated motifs that betray design or recurring behavior. When vectors were corrected for relativistic and observational effects and mirrored where appropriate, the arcs lined up in ways that statistical randomness did not comfortably explain. Some scientists began to speak, quietly at first, about a repeating cadence, probes launched or ejected in a sequence, visiting systems according to a timetable or pattern too precise to be dismissed as mere chance. That hypothesis, however, is not unanimously accepted. Science thrives on skepticism, and for every paper that suggested design, there were competing models seeking to keep the phenomenon inside the box of natural processes. One alternative explanation posited that Atlas is not engineered but extreme, the debris of a cataclysmic event in another system. Imagine a planetary collision or a star-neighboring supernova that hurls material into interstellar space, where only the most unusual volatiles survive. In this model, the carbon dioxide-dominated chemistry reflects formation in frigid circumstances, where CO2 froze before water did, and the nickel abundance hints at fragmentation of metallic bodies rather than primordial cometary composition. The sunward jet could then result from exotic sublimation physics under intense stellar irradiation, a process we have not observed because we lack a sample of objects formed under those conditions. Such an explanation retains naturalism at the cost of invoking volatiles and structural behaviors beyond our current catalog. There is also the issue of instrument anomalies. Around the same time the plume was being studied, several observatories reported temporary glitches, signal dropout events, and brief interruptions of data flow that correlated with pointing at Atlas. These anomalies were subtle, repeated, and specific to certain frequency windows, the very bands used for deep space telemetry and high-fidelity imaging. Some teams reported brief increases in background noise, others observed transient delays in data transfer, and a few recorded spurious readings in spectrographs. They were not catastrophic malfunctions. They functioned normally when observing other targets. The pattern raised uncomfortable questions. Was Atlas passively interacting with our instruments or actively probing them? If an object were designed to sense technology, to detect instrumentation, and to test our responses, those small electromagnetic fingerprints might be one way of doing it. Think of it not as broadcasting in our direction, but scanning for signatures of observation. How we point our telescopes, what frequencies we use, how quickly we react. The glitches could be diagnostic, not communication in any human sense, but a way to map the degree to which its observations are noticed. In this framework, Atlas is less an attempt at contact and more an assessment, the cosmic equivalent of a scientific instrument checking whether a planetary system has the capacity to detect and interpret anomalies. Adding to the public anxiety was the realization that the detection capabilities of Earth are changing fast. The Verisi-Rubin Observatory was ramping up operations, and its combination of deep, wide, and fast survey capability promised to send the number of detected interstellar intruders skyrocketing from 1 in a decade to many per year. With more eyes and smarter software, AI-assisted detection routines now combing terabytes per night. Objects that previous generations would have missed are now being cataloged, measured, and analyzed in real time. That should be cause for celebration. More data, better models, a richer understanding of the galaxy's inventory. But in the context of Atlas and similarly strange cases, it also means we might be seeing the tip of an iceberg. Dozens of minor anomalies that, when stitched together, reveal a fabric of activity crossing our solar neighborhood. When you begin to connect the dots, the picture becomes harder to keep in the bounds of surprise. Some scientists began to construct hypothesis spaces that incorporated multiple interstellar sightings into an interconnected web. Trajectories that at first seemed random coalesced into plausible tracks that threaded through the solar system with geometric precision only discernible when viewed through high-resolution, long timescale datasets. Rather than isolated intruders, these could be nodes in a larger structure, a galactic scaffold, a lattice of observation points left by agents whose timescales transcend human centuries. If true, the implications are staggering. We are not alone in the sense that we share a galaxy with other matter and energy. We are being observed by objects whose behavior hints at intentional placement. Of course, this kind of claim invites extraordinary scrutiny. Extraordinary claims demand extraordinary evidence. The science community reacted accordingly. Teams replicated analyses, requested independent data, and demanded open sharing of raw observations. Peer review and duplication, the bedrock of scientific validation, kicked into gear. Simulations that incorporated directed thrust, anisotropic mass loss, and heavy particle emission were run on supercomputers for weeks. The results were awkward. Only by allowing models to include purposeful, directional emissions did the data consistently match observations. When randomness was enforced as a strict assumption, residuals persisted. It's a sobering moment when nature refuses to reconcile with the simplest models, and the next likeliest explanation is purpose. The narrative inevitably spilled into the public sphere. Headlines across papers and feeds used language that alternated between wonder and dread. Commentators debated the odds of alien probes. Online forums exploded with speculation about covering moons with reflective tarps and sending radio messages to strangers in the sky. Agencies like NASA and ESA were careful in official statements, reiterating uncertainty and caution. Yet, beneath careful bureaucratic language, a new kind of existential consideration began to infiltrate conversations among policymakers, ethicists, and even defense analysts. If objects are intentionally surveying star systems, what are the protocols for interaction? Does observation warrant a response? Should we attempt to alter the trajectory of an interstellar object? Who decides? There is, of course, a long and thorny history of protocols and procedures in the scientific community about encountering extraterrestrial intelligence. SETI protocols, international frameworks, and working groups exist to advise governments on first contact scenarios. But Atlas is not a message in the clear sense. It is not sending Morse code or radio beacons. It is a physical phenomenon that reads like a question. How should humanity respond to a probe that observes but does not speak? The debate quickly polarized between those urging restraint. Do not act hastily. Ensure any responses are multinational and carefully considered. And those arguing for contingency planning. Prepare to observe, communicate, and, if necessary, defend. There are also practical considerations rooted in risk assessment. If an object maneuvers in ways we cannot monitor during solar conjunction, could it alter its course to pose a threat to planets or satellites? The probabilities of direct impact remain vanishingly small. The energy required to turn an interstellar pass into an Earth collision is enormous. Yet the fact that an object could execute an undetected burn while hidden behind the sun raises concerns about strategic surprise and the integrity of planetary defense monitoring. Agencies responded by refining blackout contingency protocols, harnessing radio observations from spacecraft in other parts of the solar system, and coordinating to keep a watchful eye during the critical conjunction period. Then came the human element. Scientists at observatories and universities found themselves at the center of a cultural event. Emails turned to encrypted chats, shared data streams flowed between institutions, and the once arcane practice of orbital reconstruction entered late-night trending topics. There was exhilaration and fear, not always in equal measure. Young researchers thrilled at the possibility of contributing to a discovery that would be taught to future students alongside the names of Copernicus and Huygens. Older colleagues, weathered by years of subtle discovery and false dawns, urged caution and rigorous skepticism. The tension between wonder and discipline, between hope and method, became part of the story itself. As October 30th approached and Atlas slid into solar conjunction, observers could do nothing but watch history being made in reverse, a bright anomaly becoming invisible under the very star that gives us light. Instruments switched to protocols designed for loss of visual contact. Teams prepared for long gaps in telemetry. Simulations prepared for every conceivable post-conjunction scenario. The question was simple and terrible. What will happen behind the sun? It could be nothing at all, a pause, a trick of optics, a natural process that finally yields to a more complete model. Or it could be something decisive, a maneuver, a reset, a new trajectory that would only be observable once the object reemerged. When Atlas reappeared on the other side of the sun, the initial observations were the kind of collective breath-holding that rarely happens in science. Eyes scanned the same arcs, instruments gathered spectral snapshots, and algorithms compared new positions to older predictions. The world waited for a sign. The same plume oriented sunward, a change in velocity, any evidence that the object had taken advantage of its secrecy. What emerged was both anticlimactic and revealing. Some parameters shifted slightly. The most telling change was a subtle redirection consistent with a small propulsive event. It was not dramatic enough to provoke immediate alarm, but it was significant in a way that meant the decision to allow uncertainty and observation rather than intervention had real consequences. The interpretations post-conjunction were as fractured as the community itself. Some pointed to the small course correction as proof of autonomous propulsion. Others countered that the change was within error bars for extreme sublimation models. The truth, as is often the case in science, sat in the gray. What was undeniable, though, was the fact of continued observation and debate. More objects were detected in the months that followed, some bearing odd signatures, some perfectly ordinary. Among them, at least one candidate appeared to have no coma at all, a cold, dark nucleus gliding in from the interstellar depths. The sample of interstellar visitors was, for the first time, large enough to start meaningful statistics. Patterns could be weighted, anomalies could be compared, and emergent properties could be identified. Looking back, the episode forced a cultural recalibration. We designed telescopes to see outward and probes to travel outward, but we had not built a framework for being the subject of observation at this scale. The galaxy, once pictured as a quiet expanse with the occasional random rock, now looked busier and possibly intentional. Weather Atlas and its kin were artifacts of a technology far older than humanity, the detritus of violent cosmic events, or something in between. The revelations transformed the way we think about cosmic neighborhood planning, planetary defense, and the ethical dimensions of interstellar curiosity. The significance extends beyond the immediate physics. If probes roam the galaxy to observe emergent intelligence, and if they time appearances to re-emerge when they judge their sensors to be effective, then humanity has crossed an invisible threshold. Detection is not merely a technical achievement. It is a cultural turning point. Our telescopes are not only instruments of discovery, they are the triggers for responses we cannot fully foresee. We are compelled to ask hard questions about secrecy, about how to respond to phenomena that may be monitoring our technological signatures, and about the responsibilities of a species now visible to a wider cosmic audience. Even if future data ultimately resolve Atlas into a natural class of extreme interstellar bodies, that outcome would be no less profound. Discovering a new natural category of objects with CO2, dominant chemistry, high nickel content, and directionally focused sublimation would rewrite planetary formation models and enrich our understanding of the diversity of materials across the galaxy. It would prompt new searches, new lab experiments, and new models for chemistry under conditions we have yet to replicate. The natural world often surprises us by producing behavior that seems engineered simply because our imagination is inadequate to the diversity of physical processes. The universe is larger and stranger than our metaphors. If, on the other hand, the engineering hypothesis gains further support, if Atlas and others are confirmed as autonomous probes, then we are faced with questions of a different order. What are the intentions, if any, behind their presence? Are they one-off artifacts from a civilization long gone? Are they part of a monitoring program, a galactic census? Are they instruments of benign curiosity? Or are they components of a more complex system that tests and catalogs nascent technologies in other star systems? Answering these questions would strain the limits of both our science and our diplomacy. For now, the prudent path is to keep looking, to refine our instruments, to broaden international collaboration, and to build protocols that allow for a thoughtful, measured response to further anomalies. The coming years will be a time of both excitement and caution. Rubin and other survey telescopes will flood the community with detections, and data science tools will parse those detections for anomalies. Collaborative networks will continue to compare observations across wavelengths and platforms. And behind the scenes, ethicists, policymakers, and scientists will debate how to manage the social and existential dimensions of observation at the interstellar scale. The arrival of 3I/Atlas served as a mirror, one that reflects not only the object but ourselves. It asked how we handle surprise, how we integrate unsettling data, and how we balance curiosity with caution. It reminded us that advancing technological capacity brings visibility, and visibility invites response. Whether Atlas is a natural time capsule, an engineered scout, or something that defies both categories, it pushed humanity into a new conversation about our place in the cosmic environment. The story is not concluded. As more eyes sweep the heavens, more anomalies will be uncovered, some mundane, some strange, some revealing. Each new object will test our models, our biases, and our protocols. Whether these visitors become a thread that unravels into a tapestry of deliberate watchers or a cascade of newly discovered astrophysical phenomena, the result will be a richer, more complicated picture of the galaxy and our fragile, attentive place within it. In the end, what Atlas offers may be less a message than an invitation. Look harder, question the comfortable narratives we construct about the universe, and be prepared for the possibility that we are no longer merely the observers, but also the observed. That recognition changes the way we design instruments, the way we write policy, and the way we think about stewardship of our planet and our signals. The cosmos has always been vast and indifferent. What Atlas suggests, if it suggests anything at all, is that indifference may be more complicated than we thought. Maybe in the quiet elegance of a sunward jet, in the stubbornness of a spectral line, in the timing of a conjunction, the galaxy has been nudging us toward the realization that being seen is itself an event of consequence.